extension of Cauchy's integral theorem. Or Cauchy's integral formula. So, in other words, we want to find something like this. What if you have f of z dz over, say, z minus z naught into z minus z1 all the way up to z minus zn? You could have many factors at the bottom here. So how does one handle a situation of that type? Contour integral along some curve C. For example, let's take a simple example where we have just three of these things. F of z over z minus z naught, z minus z1, z minus z2, dz. Okay, so watch this trick here that we can employ. Let's take our 3 points, z naught. Let's take the 3 points, z naught, z1, z2 on the plane. Z naught, z1, z2. Here are the 3 points. Assuming they are in a domain now and it's simply connected, there's no poles nearby it. So what the trick is, you surround each of these guys by a circle. You notice I'm leaving a small gap there. It doesn't have to actually be a circle, but if you take a situation of that, then you have these small tubes here. Right. This is a nice picture. Your kindergarten brother or somebody will enjoy drawing this. And then you join these here. Now, you may be wondering, what's going on now? Why did you do that fancy trick? Well, now we've created a region gamma that is holomorphic, and those bad boys are no more in the region. Check those Z0, Z1, Z2, it doesn't lie in gamma. So f of z is completely holomorphic in gamma. I neatly avoided those guys. And also, if you look at the big curve outside, let's say that is anti-clockwise. Okay? So when you come down here, it's anti-clockwise. When you go into the loop here, a tube, that direction there is like that. Then you go inside the thing there, the circle. Oh. But now inside the circle, you see the thing has changed. Now it's become clockwise. Whereas the big thing has got anti-clockwise behavior. So anyway, and also on these tubes here, you see first you go in and then you come out. When you do the integral along that piece, one will be positive, one will be negative, they'll kill each other. That's really what's going to happen there. We carry on with these arrows, inside, go around. You see that's clockwise. Then you got those two killing each other, go around, go inside, go around, clockwise again, come out. Those two tubes, things kill each other there. So we surround each Zn by a circle with thin tubes, as shown. So we create gamma, which now excludes Z0, Z1, Z2. Now, since there's no Z1, Z0, Z1, Z2 in gamma, the contour integral of f of z over z minus z naught, z minus z1 into z minus z2 dz will be 0. That's the Cauchy-Gaussian theorem. It's a complete curve. The contour integral is 0 because inside there's no bad boys. Cauchy-Gaussian theorem tells us that the contour integral is going to be 0. I've drawn your attention to the fact that some are counterclockwise and some are clockwise. So just jot this down. Note that C is anti-clockwise. C is this entire curve, anti-clockwise. But these curves, let me call them C0, C1, and C2. The ones that are surrounded the Z0 by. But C0, C1, C2 are clockwise. Hence, this contour integral of f of z over z minus z0, z minus z1, z minus z2 dz minus, now each of them, you're going to subtract each of those guys. Why subtract? Because it's anti-clockwise. Now I'll just use mathematical language. Instead of writing all three guys out separately, I'll say the sum of these guys here, f of z minus along each c k. Did I use k? Yeah, k. From k equals to 0 to 2. There's three of them, 0, 1, and 2. I'm just simplifying this. Z minus Z0, Z minus Z1 into Z minus Z2 dz is equal to 0. That's the Cauchy-Gaussian theorem, yes? No, so we are adding all of, so the big C is a great one there, and then you remove those middle guys. So the big one has got a positive sense of rotation. Basically, you have to add all four pieces: the big C and those four small ones, three small ones. That gives you 0. So but when I say add them, actually you have to subtract them because they are anti-clockwise. I mean, they go in the wrong direction. That's why it's minusing those bits. Yes? Oh, gamma is a region. C is a circle, is a curve around it. Yeah. The path. C is the path and gamma is the region. Anything else that's not clear? I thought this cryptic notation might be not clear, but really I'm subtracting C0, C1. I'm subtracting the path. Basically, I'm adding it, but really it becomes subtraction because the direction is wrong. So when we have C0, C1, C2, the integral to C1, C0, the integral to C1, and the integral to C2. But now we have tools to handle it. So if you transfer, you can say that the integral, this is now the extended formula, f of z over z minus z0, z minus z1 into z minus z2 dz along a curve C is actually the sum of k equals to 0. You can actually have n here. I'll just write it as n, f of z over z minus z0, z minus z1, dot, 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 up to z minus zn, dz. You can have as many of those holes as you need. Doesn't matter how many of these factors you have. You have to add them up. So the contour integral along C is the sum of the contour integrals along each one. That's the model of the tail. This is the extended CIF. Recall earlier I argued that you can do the same thing with partial fractions. You can split up all those things into partial fractions. Then it means something. Partial fractions tells you can actually split them up into little pieces by themselves. And this is exactly what we are saying here. But our argument here is based upon the contour going backwards. That's how you get the minus on the left-hand side. And the contour integral being 0 follows from Cauchy's, the Cauchy-Gaussian theorem, which tells us if the function is completely holomorphic in the region, the circle integral is 0. Now I said the circle integral is made up of the big piece there and those other three small pieces. I put them together, that's supposed to give you 0. How the minus enters? Because of the wrong direction. Second example. Let's just take, find, let's say tan z over z squared minus 4 dz, where C is z equals to 5, let's say. Now we've got z equals 5 is a circle of radius 5. And denominator equal to 0 implies z squared minus 4 is 0. Therefore, z equals to plus or minus 2. Both are real numbers. 2 is there, minus 2 is there. Now we have a situation where both lie inside the contour. Both lie inside a closed path. So the Cauchy-Gaussian theorem doesn't work now because it's not fully holomorphic inside that region. There are some points which are badly behaved. But we now know the method to handle it. So the solution, I can write the integral of tan z over z squared minus 4 dz as the integral of tan z over z plus 2 into z minus 2 dz. And then I disguise him as integral of, well, you see let's write it as tan z over z plus 2 when z equals to 2 plus, actually it's 2 pi I times this, plus tan z over z minus 2 at z equals to minus 2. First we put this guy on top. This guy here. Everything except z minus 2 because I want to work out the value at z equals to 2. So block z minus 2. That is f of z. What you see there is f of z. Then for that side, I want to see what happens z equals to minus 2. So block z plus 2. That's how you get minus 2, by the way. So tan z over z minus 2. And I just have to substitute minus 2 there, and I'll be done with the integral. There's no integration. That's the beauty of this entire theorem. There's 2 pi I. Just substitute now z equals to 2, so it'll become tan of 2 over 2 plus 2, 4, plus tan of minus 2 over minus 2 is minus 4. It's 2 pi I tan of 2 over 4 Well, this will be plus minus tan 2 over minus 4. What's that like? Half of tan 2 plus is half. It's 2 pi I times tan 2 over 2. So it's pi I tan of 2. Well, this comes from the theorem. The theorem said that the integral is 2 pi I times f of z naught. Remember Cauchy's integral theorem? It says integral of f of z over z minus blah blah blah. Okay, z minus z naught equals to 2 pi I times f of z naught. Now we're saying that it's 2 pi I times f of z naught plus f of z1 plus f of z2. Doesn't matter how many so-called points where I'm avoiding the word that we will be using next is pole. At the denominator, those points at the denominator become 0, we call them poles. So where those poles exist, that's how many times you've got to sum them. Any questions? Now the problems can get quite tricky, and they will in tutorials and the exam. You see, the first part of this here is to work out the poles where the denominator equals 0. That's a very innocent, easy problem. Z squared minus 4 equals 0. I'll bet if I put z squared minus 4i equals 0, you will be totally bamboozled. If I write z squared minus 4i equals 0, how would you do that? Now you'll have to hit that with the Morgan's theorem. So that will be half a problem itself. We'll come across something like that, I think. Oh, here's one here. This one, I'm not going to finish this problem for you. I finished it at home, but it's tedious. It's meant for you to finish, really. Well, I actually didn't finish to the end, but I'll tell you where you can logically stop in a test or an exam. We don't expect you to go right to the end because it's tedious computations. I'll just make up an example. Find contour integral of z over z cubed plus 1 dz, where c is the square, absolute x plus absolute y equals to 4. Earlier on, we gave you a cardio. Flashback to first year. When you're learning all the stuff in first year, you're wondering why are they teaching us all this kind of things. Can be everything useful. Now you see this life comes to the picture. In first year, we also taught you how to draw things like that. Absolute x plus absolute y equals 4. Remember how to do that? When you reach third year, you're supposed to just do it from remembering the first year stuff. They don't teach you this from scratch. How do you draw that? This will be the first thing in the exam questions. Before you actually start computing something, you have to analyze what the given stuff is. So, I think firstly, let's take both x and y being positive. X plus y equals 4. There's two absolutes. Let's take them both positive. X plus y equals to 4. That'll give you a piece of line like this. Let me draw it bigger. So you get a piece of line like that. X plus y equals 4. If x is negative and y is positive, it'll be minus x plus y equals to 4. Then you get another piece somewhere there. Then you take x positive and y negative. Get a piece somewhere there. Lastly, both negative. I could be wrong in the order in which I said it, but you get the idea. So that's the square. X plus absolute x plus absolute y equals to 4. Each one can have a term to be positive or negative. There are 4 options, and they give you the 4 sides of a square. Now, the next task here is to work out whether the denominator is 0. Solve z cubed plus 1 equal to 0. Or we can say z cubed equals to minus 1. One root is known. What's one answer? Everyone should know. Which number cubed gives you -1? -1. -1 times -1 times -1 does give you -1. So that's one root. When you do the work, you're supposed to get that root as one of the answers. That will confirm to you that it's correct. But how do you get the other two roots, guys? This question has two roots, two options. You can hit this with the Morvis theorem, which I'll show you now. Or you can use the factorization. Z cubed plus 1 is Z plus 1 into Z squared plus Z minus Z squared minus Z plus 1. Then use the quadratic formula for that part. Bit of a schlep there. But that's another way of doing it. Let's go with the Morvis theorem because you can use this more often in calculations. Right? So you can use the Morvis theorem. So you can say Z cubed equals to -1. Actually, it's okay, it's -1 plus 0i. -1 plus 0i. So if you have to plot this on a plane, the point -1 is here. Okay? So you need to know what is the angle that applies there and what is the radius. The angle that applies is how many degrees or how many radians? For -1, what is the angle to get here? Pi. Let's call it pi. So the theta is pi and the radius is 1. So you can say this is the same as cos of, well, it's 1 of cos pi plus 2k pi plus I sine of pi plus 2k pi. The angle is pi. But remember, this happens every 2k pi. It goes around 2 pi many times by 2 pi units. And then if I want to get z to the 1/3, it'll be cos of pi plus 2k pi plus I sine of pi plus 2k pi. I'm just doing this here like baby class first year because I suspect you forgot how this works. I'm just trying to refresh your memory. Put the power 1/3. Z cubed goes on the side becomes the power 1/3. Now the Morvis theorem tells us you put that inside the bracket. So it becomes cos of pi over 3 plus 2k pi over 3 plus I sine pi over 3 plus 2k pi over 3. That's the Morvis theorem. The 1/3 goes into the bracket here. You divide the angle by 3. We've done this before. You can remember the first lectures on complex, we started off with this. I did refresh your memory. So if you want another example, go back in the book and see how I did those examples. So let's find the 3 roots now. There should be 3 roots. And remember I told you when we did this properly in class that when you plot the 3 roots, what will the 3 dots form on the coordinate plane? Equilateral triangle, yes. They will be equally spaced in a circle. When we plot them, but we're not going to do all that now. That's very nice stuff. But all we need is the 3 roots here, right? So Z naught will be when k is naught. So it'll become cos of pi over 3 plus I sine pi over 3. Cos 60 plus I sine 60. What's cos 60? Half. Plus I sine 60 is root 3 over 2. So that's the first root. Half plus root 3 over 2i. Z1, if you put k equals to 1. So that's 1/3 plus 2/3 pi. That's just pi. Cos pi plus I sine pi. Cos pi is -1. Sine pi is 0. And that's the root I said we know already. -1 plus 0i. And Z3 is cos of, now put k equal to 2 here. That's 4/3 plus 1/3 is 5/3 pi. Cos 5/3 pi plus I sine 5/3 pi. Cos 5 third 5 is like 5 times 60. That's 300. That's in the fourth quadrant. Cos of 60 in the fourth quadrant is half. But sine of 300 degrees is minus root 3 over 2. So those are the three roots. You don't believe it, you can cube each one and you'll get minus 1 for each. If you cube each of these guys here, the answer will be minus 1. I know you can't wait to go home and try that out, just to see if it works. Every diligent student does this, and I know you will do this as well. No, I'm serious. I know you will have that willingness to go and check this out. Okay, anyway, those are the three roots. It's going to look a little messy now, but hey, who said things have to be easy? Now, when we plot these three roots, guys, in the plane here, one of the roots is minus 1. That's the one that's there. Then another one is half plus root 3 over 2. The coordinates are half and root 3 over 2. The question is, does it lie inside the line or outside the line? Well, I made this thing so big. I mean, I gave it like a radius of 4, you could say, so that it will be very clear that this thing lies inside. If it's not clear, you have to test it. How do you test it? You have to use a distance formula and check whether it lies inside the square or not. But I don't want to do all that in an exam, so I'll make it very obvious. I'll make the square big enough if I set a question like this. So you don't have to check it. By intuition, you know it lies inside. And the third one, of course, will be here. That's purely by symmetry. Half minus root 3 over 2. And as I said, they do form an equilateral triangle. The third one you can get by just knowing it's an equilateral triangle. If you just reflect the top line down here, equilateral triangle. You can get this in many ways to save yourself time. That's if you are agile as a mathematician. You know many things backwards and forwards. It can make your life easier. All right, now, tragically, the game gets a bit dirty because you've got this funny factors here. So the factors are z plus 1. That's a nice easy one. Z minus this guy here. Z minus this guy here. That's quite dirty. So integral of what is on top? Z. Z over Z cube plus 1 dz along this part C actually becomes integral of Z over Z plus 1 Z minus half minus root 3 over 2I into Z minus half plus root 3 over 2I. That's the dirty part I was telling you about along C. So now you've got three items, Z minus Z naught, Z minus Z1, Z minus Z2. You sum each one. So for the first one, let's say I want to work the thing out at minus 1. I block Z plus 1. What you see left there is f of Z. As ugly as it looks, that it is. So the first thing would be, sorry, the theorem says it's 2 pi I times. So the first one will be block Z plus 1, so you get Z over what's left, Z minus half minus root 3 over 2I into Z minus half plus root 3 over 2I. And you need to substitute Z equals to minus 1. In that, we block Z plus 1 for the Z minus 1 thing. The rest of it is f of Z. So now you're going to find f of Z naught, but plugging in that so-called singularity or pole. Now the second one will be Z over let's go for this one here. half plus root 3 over 2i, the first one. So let's block this factor here. Let's block this guy here. Then what's left becomes f of z. Z over z plus 1 into z minus half plus root 3 over 2i. And we are going to substitute z equals to half plus root 3 over 2i. Lastly, I want to deal with this guy here. I block this guy. And what's left is z over that. That becomes the last f of z. It becomes z over z plus 1 into z minus half minus root 3 over 2i. And I must substitute z equals half minus root 3 over 2i. Messy, messy, but so I don't expect you to complete this right to the end, but I do expect you to put the substitution in and stop. You should substitute, but not compute it, because it's not tedious to substitute. 2 pi I into, so first you put z equals to minus 1, so you put minus 1 there, then you put minus 1 here. Minus 1 minus half is minus 3 over 2. Minus 1 minus half is minus 3 over 2. Where am I? No, I missed something out. Minus 3 over 2 minus root 3 over 2. And when I plug in minus half here, it's minus 3 over 2 plus root 3 over 2i. That's a sum and difference. Actually, that becomes quite nice. It's 9/4 plus 3/4. That's 12/4, which is 3. Actually, this big guy here is just 3, minus 1/3. But don't worry, I mean, it takes time to see that. Plus, now in the next one, I must plug in half plus root 3 over 2i. Change the color here for you. So you put half plus root 3 over 2i. At the bottom, z plus 1 becomes 1 plus half. So it's 3 over 2 plus root 3 over 2i into. Now, half plus root 3 over 2i. Half minus half is 0. Root 3 over 2i plus root 3 over 2i is root 3i. So here you get a humble root 3i plus. In the end here, you substitute half minus root 3 over 2i. And then this becomes half minus half is still 0. Minus root 3 over 2i minus root 3 over 2i is minus root 3i. Oh, where's the z plus 1? So it's 3 over 2 minus root 3 over 2i. So if you pause at that stage, then that's okay. But really, any student worth his salt will go home and finish this off. But for the purpose of an exam, I wouldn't expect you to go to the end. I expect you to substitute and stop. I will look for that. We don't allocate marks to the final answer. We're never unreasonable, as you know. Oh, that's the last one. Okay, finish 6 minutes later. You want to stop? Stop. Can we stop? Okay, I think we shall stop here. Any questions before you leave? You can ask me privately also if you're feeling shy.